Hello and greetings to everyone. We are from Group 1-3. We'll be presenting an integrated design project entitled Hydrogen Production using Steam Methane Reforming Technology. Our group consists of 5 members, which are Aminah, Solehah, Al-Imran, Saidah, Farzanah and also Sinesh.
Assalamualaikum and hello, I'm Farzanah Hannani, and for this integrated project, I'll talk about the overview of hydrogen production using SMR technology and also explaining part of CEB 2043 reaction engineering. SMR technology is most commonly used in hydrogen production as it is more efficient and feasible. The technology can achieve high purity of hydrogen at low cost. The first reaction is steam methane reaction, where natural gas containing methane react with steam at high temperature to produce hydrogen and carbon monoxide. Since carbon monoxide is harmful to environment, steam methane reaction is accompanied with water gas shift reaction, whereby the carbon monoxide produced is then react with excess steam to produce carbon dioxide and hydrogen. The shifted synthesized gas is then will undergo CO2 removal and H2 enrichment to purify the gas. Now in this topic, I will explain about the reactor design and catalyst used in the reaction. In this part also, I will explain about the strategy to maximize hydrogen yield and selectivity. First, let's revise again the reaction. In SMR reaction, it is endothermic reaction between methane and steam to produce hydrogen and carbon monoxide. The second reaction is WGS reaction, an exothermic reaction between carbon monoxide and steam to produce hydrogen and carbon dioxide. Both reactions are catalytic operation that requires catalyst. For SMR, the catalyst used is nickel-based catalyst that is supported by aluminum 2 oxide, while for the second reaction, which is WGS reaction, the catalyst used is ferrum 3 oxide that is supported by chromium oxide. These catalysts were chosen as they exhibit good reactivity and no agglomeration while has economic value. Since both catalysts used are in powder form, which is solid, thus the suitable reactor design will be packed-bed reactor. Since the reactor is packed-bed reactor, there is continuous flow. Therefore, the selectivity and yield of hydrogen can be maximized with higher flow rate of hydrogen. To increase the flow rate, we apply Le Chatelier's principle, which states that if a dynamic equilibrium is disturbed by any changes in its condition, the position of equilibrium shift to counteract the changes to re-establish an equilibrium. The changes can be by temperature changes, pressure changes, or changes in concentration of reactants or products. The first strategy is to decrease the pressure of SMR. Based on Le Chatelier's principle, when the pressure is decreased, counteract will happen to increase back the pressure by shifting the reaction towards the product side. Hence, there is increment in hydrogen production. However, the pressure must not be lower than 20 atm. The next strategy is to decrease the temperature of WGS. Since the reaction happen in WGS is exothermic, decreasing temperature of reactor will make the equilibrium to shift towards the product side in order to increase the temperature back to its original state. Thus, hydrogen production will increase. However, the lowest temperature of the reactor must be at 200 degrees Celsius. To have higher production of hydrogen also, we can increase the concentration of methane. If there is higher concentration of methane, the reaction will favor in which the species is consumed, hence more hydrogen will produce. Other than apply Le Chatelier principle to increase the yield and selectivity of hydrogen, we also can manipulate the steam to methane ratio. The range of SC ratio can be from 1 to 5. With higher ratio, more WGS reaction will be triggered. That's all from this topic. We'll move on to another topic. Thank you.
Next, moving to the process modeling and simulation section, the reactor system design in the previous reaction engineering part is being simulated using symmetry software with few important assumptions, which includes first, steady state reactor system. Only pure methane exists in natural gas stream. The thermodynamic package used is advanced Spang-Robinson, and the order of reaction is first order, while the type of reactor is plug flow reactor. On top of that, in order to validate the simulations, few variables are chosen and compared by evaluating the deviation error with manual calculated value, which are outlet mole flow rate of hydrogen, total flow rate, yield, and also the selectivity. In SMR reactor, the mole flow rate of hydrogen shows a deviation error of 31.38%, while the total flow rate only shows 6.34% of error. Meanwhile, the yield and selectivity shows 0 error. In WGS reactor, the mole flow rate of hydrogen produced show a deviation error of 20.53%. Meanwhile, the total mole flow rate, yield and selectivity shows a deviation error of 0.38%.
Hi, my name is Aminah Solehah. For this section, I will explain on the sensitivity analysis part of process modeling and simulation. Sensitivity analysis is to evaluate how different values of an independent variable affect a specific dependent variable under a given set of assumptions within certain boundaries that are dependent on one or more input variables. This strategy is applied. In this section, the sensitivity analysis focuses on the effect of temperature, pressure, feed mole flow, and composition towards the reactor performance, represented by the mole flow of hydrogen and carbon dioxide produced at the outlet of reactor. The first one is the effect of temperature to the mole flow of carbon dioxide and hydrogen. For the first 5 points, it can be observed that both mole flow of carbon dioxide and hydrogen at CO2 removal are constant. However, at the 5th point, both mole flow started to show increment. The increment of hydrogen mole flow trend line seems steeper than the carbon dioxide mole flow. It is because of the rate of mole flow of hydrogen is higher than the carbon dioxide. Next is the effect of pressure on the mole flow hydrogen and carbon dioxide at CO2 removal. Based on the graph shown, both mole flow of hydrogen and carbon dioxide does not undergo any changes through the trend line. The pressure increasing did not affect the changing in mole flow of hydrogen nor carbon dioxide. Although there is slightest changes in the mole flow of hydrogen and carbon dioxide alongside the increment of pressure, but it does not affect the mole flow that much. Thus, it can be assumed that the changing is approximate to zero. Third, the effect of changing feed mole flow towards the mole flow of hydrogen and carbon dioxide produced. As the feed flow into the reactor increases, the mole flow of hydrogen increases while the mole flow of carbon dioxide also increases. The outlet flow of hydrogen and carbon dioxide is directly proportional with the feed flow rate. Increasing the feed flow rate will increase the outlet flow rate of a reactor. In this reaction, hydrogen gas is the desired product while carbon dioxide is the undesired product and need to be removed to achieve high purity of hydrogen gas. The last one is the composition of carbon dioxide on the mole flow of hydrogen and CO2 produced. As the composition of CO2 varied, the mole flow of CO2 increases while the mole flow of H2 decreases. Both mole flow shows an opposite trend between each other. Mole flow of carbon dioxide and mole flow of hydrogen reach equilibrium mole production at 0.7.
Next, we will move on to separation process 2 part.
Alright then, so therefore, there is two types of absorbents, which are activated carbon and zeolite 5A. So let's begin with activated carbon. Activated carbon, or commonly known as activated charcoal, can be seen in many products today, which can be useful as a very useful absorbent. Okay, the types of activated carbon consist of granulated, pelletized, powdered, impregnated, and catalytic activated carbons. The reason for having different types and sizes of activated carbons is it designated for different purposes for different contact time, as it is used to determine the suitable material and application to be conducted. Whereas for zeolite 5A, you can see that it is a very effective absorbent which is used to remove hydrocarbons and heavy metals. Okay, the advantage that it can be seen in the zeolite is in its physical structure, where it is able to bind to heavy metals and the hydrocarbons. Not only that, the zeolite is naturally able to carry up to 60% of its own weight in water and 30% of weight in oil. Alright, so for the second one will be types of adsorbent isotope that we use. So as you can see, there will be one that will be the Langmuir isotope. Okay, what is the Langmuir isotope? It is the maximum amount of gas that a shell can hold at a specified pressure and temperature. Alright then, so let's focus on the next slide, which is about the strategy to achieve 99.9% purity for hydrogen production and desorption processes, which consists of PSA for hydrogen, hydrogen selective membrane, equal pressure, low temperature, and adsorption time. So for the PSA for hydrogen is where the usage of syngas to produce the hydrogen, where there will be use of multiple layer beds which are absorbers like activated carbon and zeolite, which use the because of the purification is achieved up to 99.9% and it's up to 60 to 95% recovery which can be achieved. The most common type is the 4-bed PSA, which produces the highest purification with the most efficient energy. As for the hydrogen selective membrane, polymeric membrane is the most common type membrane which is able to function temperature below 100 degrees. Okay, whereas the second type is the metallic membrane, which can withstand up to 300 to 700 degrees Celsius. Whereas the difference is for the metallic membrane is able to achieve higher selectivity of hydrogen, whereas for the polymeric membrane it is able to withstand high pressure drops but has poor selectivity of hydrogen. For the equal pressure, this is where there is equal amount of pressure applied to the directed bed or flow of the stream, which can be seen in the designated column, where the amount of pressure is equal to the previous column. This will increase in the pressure will cause the purification process to hydrogen to increase, but it is determined later that the recovery process for the hydrogen is very low. So for the low temperature, the process is called cryogenic separation, where purified hydrogen is derived from syngas. The difference in boiling point will help to separate the different compounds found, which will leave the hydrogen to be in gas phase while the rest to be condensed. Okay, next will be the absorption time. This can be seen where the long period of time is given for the adsorption to take place. The purity of hydrogen will decrease, but the recovery of the purified hydrogen will increase. Therefore, it is certain that the total absorption time is to be reduced so that the purity of hydrogen can achieve 99.9%.
Greetings everyone, my name is Imran Mansor and I will be explaining the design of the adsorption column part for separation process 2. For construction material, we have chosen low carbon steel with epoxy coating because the low carbon steel has a high tensile strength to withstand high pressure differentials. Moreover, low carbon steel has a low carbon content which makes it very malleable and more cost effective. In addition, low carbon steel will be coated with epoxy to avoid rusting and corrosion during adsorption process. On the other hand, we have utilized a 2-bed 6-step pressure swing adsorption system in the hydrogen enrichment unit due to its better PSA performance in terms of hydrogen purity, recovery and productivity as compared to a single bed system. The 6-cycle configurations started with feed gas pressurization before allowing impurities to be adsorbed. Then, the pressures in both beds will be equalized, which then being used to purge the bed at step 5. Lastly, the column will be pressurized back at the final stage of this cycle. Next, we will be moving on to the scale-up design calculations, where mass transfer zone is calculated based on breakthrough curve obtained from literature. Since layered bed design is utilized for this column, the mass transfer zone for activated carbon and zeolite 5A are calculated separately. As for activated carbon, breakpoint time and adsorption time is first determined from breakthrough curve. Then, height of used bed can be calculated by multiplying Tu over Tt with the activated carbon layer length, which is 65 cm. Lastly, mass transfer zone, or known as unused bed, can be determined, which is 31.09 cm. Meanwhile, for zeolite 5A, breakpoint time and adsorption time is also determined based on the breakthrough curve. From there, the height of used bed can be calculated by multiplying Tu over Tt with the zeolite 5A layer length, which is 35 cm. Lastly, the mass transfer zone, or known as unused bed, can be determined, which is 10.37 cm.
All in all, as we are instructed to design reactor system to obtain 30,000 tons per year of hydrogen with 99.9% of purity, the feelings that we could describe right now is that we are satisfied with everything we have done, as we have read discussion with all group members. In the first stage, we did have only a basic knowledge of the overall process. However, the outside authentic sources did help us to understand better to solve this problem. Apart from that, we are able to apply the knowledge gained from all 3 courses during lecture and also the lab sessions to solve the project requirement. And in the future, if we are encountered with the same problem, we can easily recognize the problem statement and provide solutions to solve that matter.